Hello, my name is David Schmidt, again recording for BBE 1201. This lesson is on solar energy technologies, kind of an introduction to how we capture solar energy from the sun. The sun, we think about it when we think about renewable energy, often as we think about the sun, and the sun drives all our natural cycles. It's powering our earth as we speak today because of the wind. It drives the water cycle. It drives everything that we have on Earth, all the natural cycles. It also, when we think about it, all our energy that we've talked about in the past, all our fossil fuel energy, comes from solar energy. It was solar energy that grew plants, buried underground, high pressure, high temperature, concentrating that solar energy. Because we do have a lot of solar energy, enough solar energy hitting the earth in a day to power it for a year. But because it's such low density, we can't really do anything with it. It's about 1,000 watts per square meter, which isn't very much. But we have a lot of it because our earth is big. Plants concentrate the solar energy, and they are about 1% efficient. And so that's what we're dealing with, that the plants do the best they can, but can we somehow make better use of that solar energy? And so that's what this lesson's about, is talking about technologies that we can enhance the utilization of solar energy. So when we look at the energy from the sun, then we can see that only a small section, about 44% of the energy from the sun, is actually stuff that we see. There is energy from the sun in shorter wavelengths, ultraviolet spectrum, and there is also wavelengths that are longer in this infrared spectrum. UV is what causes our sunburn, and then we have this other infrared, near infrared wavelengths that is what we feel is heat. Interesting phenomenon that we are all witness to is this short wavelength and long wavelength. So if we think about a car in the summertime, you close up the car, it gets super hot during the day when the sun is shining. What's happening is that the sun's energy is coming through the glass. The glass allows some of the wavelengths to pass. Mostly all of the visible light passes, and some of the infrared passes through that glass. Now what happens is that the energy is absorbed, the visible energy is absorbed, and the IR is absorbed by the seats and by the dashboard and everything in the car, and then it's re-radiated as heat. It's in a longer wavelength, too long to pass back through that windshield, and so it gets trapped in the car. And so that's why we are changing the wavelength, which causes this phenomenon of the car getting hotter. Getting back to our solar energy and how we use it, our sun emits lots of energy. By the time it gets to the Earth's atmosphere, it is about 1,360 watts per square meter. That's the energy density of the sun's energy hitting the atmosphere. Once it goes through the atmosphere, we're down to about 1,000 watts per square meter on average. That skies are clear, the sun is perpendicular to the Earth. Right, so that's what we're dealing with. We'll often talk about that 1,000 watts per square meter. All right, so there are variations in solar power. As we all know, when it's nighttime, there is no solar energy hitting the Earth wherever we live. If we're in Minneapolis or St. Paul, we're not going to see any solar energy hitting. Wake up in the morning and we start getting more and more solar energy, and then back to the evening where we don't have any solar energy for the rest of the day. All right, so this cycle, a daily cycle of energy from the sun. In the summer or in the wintertime, this is winter, and we get about 800 watts per square meter. That's the power from the sun, the intensity of the sun's power. In the summertime, we can see that this time period where we have solar energy is a lot higher, and we actually get more energy during that time, that noon time period. We're at that 1,000 watts per square meter. So you can already see a difference just in time of day and time of year. So we talked about power coming from the sun, watts per square meter, But what we typically like to think of is energy coming from the sun, energy per day coming from the sun. And that is in this watt hours per square meter. So we want to look at the area under this power curve. And we see obviously that this area under this curve in the summertime, June 21st, has a lot more area than December 21st. So to give you a little bit better understanding of how this works, trying to get the area under the curve is not simple. So what we typically do to graphically show this is that this area in the yellow box is the same area that's under the curve, right? And now we can see that there is a time period here, and there is a total watts here, and those are equivalent. So watts times hours per square meter equals watt hours per square meter that we get per day. All right, and we can do the same thing here. This rectangle, yellow rectangle, has the same area as what's under this red line, the area under that curve. And so we get watt hours per square meter. Typically, that's what's being reported, kilowatt hours per square meter. So we can now look at an area and look at a variation from not just day or year, time of year, but we can look at variations in solar energy from the distance of the equator and the time of year. And we can see that during the month of the year in Chicago, Illinois, we get a huge range in energy from the sun, going from 1.76 kilowatt hours per square meter per day to about 6 or a little more than 6 kilowatt hours per square meter per day. Whereas if we look at someplace more along the equator, that is a fairly flat line. So over the course of the year, we get about the same amount of energy from the sun. Right? If we look at variations in solar energy, that was based on the latitude, but we can also look at this is the same latitude. You can see this line is the same latitude, but we are getting way different amount of this graph is the annual solar irradiance or solar energy coming from the sun. And we can see that along the same latitude, there is a difference in the annual energy from the sun that we can capture because of cloud cover, primarily cloud and rain, because this is a much drier area. You don't get as many clouds. And so you're seeing more, darker red is more solar energy. This ranges from about 4 up here in this lighter yellow section to about 6 down here on average annual kilowatt hours per meter squared per day. We can see that it's not really that much. We're about 30% less solar energy that we can capture here in Minnesota than they can capture in New Mexico. So how do we utilize this solar energy? And there's a couple ways to do it. One is through passive thermal energy. We can do concentrated thermal energy, and we can do solar photovoltaics. So passive solar energy, that has been used for a long time. We understand that when we stand outside, we can feel the warmth from the sun. And so we take the same concept, same energy from the sun, we use it to heat a large mass in a home. Say we have stone flooring, and we try and capture that. So the sun is beating, sun's energy is coming through the windows. Remember what we talked about with a car? We're taking some of the visible light and trapping it in the space. All right, so we can use a passive solar thermal system to heat our home some. In Minnesota, it's not enough to heat our home completely, but we can gain heat from that. So you might have some large windows, and you might have an overhang that prevents the summer sun, which you're trying to avoid coming into your house because you don't want it heated up. But you have the winter sun is down lower in the sky, so you get the energy coming through the house and heating the house, and you have good insulation in the house. So that's the simplest way that we can use solar energy. We can then add on to this and say, here's our mass, our thermal mass right here. We're going to heat this up, and then we're going to get some circulation of air because hot air rises. It'll rise up here, and then cool down and complete the cycle. So you have a glass, the sunlight's coming through the glass, heating the panel, heating the thermal mass, and then recirculating that warm air. Once again, super simple, fairly effective, but in states like Minnesota where it gets really cold, you're not going to be able to do that and heat your house for the year. But a lot of architecture structures will play with that passive solar heating to do at least part of the heating task in the wintertime. The next passive solar system that gets quite a bit of use is passive water heating. So this is a system where there's a series of panels, black panels, painted black to absorb more energy from the sun. Remember we talked about albedo, so it's going to absorb more energy from the sun, reflect less, and then you run water tubes right on top or right below this panel, and that will then feed this hot water tank, which then can be used for hot water in the house. And then you're going to replace this hot water with cold water, and the cycle continues where you take that hot water, heat the water tank, and use that water. It actually can be used in Minnesota. There's enough heat in the wintertime from the sun that we get some solar. Some people are putting in solar hot water systems, also with backup natural gas or electricity. Taking it a next step further, we can do concentrated solar. So concentrated solar is taking solar energy, and we know that it's 1,000 watts per square meter, so not super dense. Can we focus it down into an area where we get more beneficial energy? And when I talk about more beneficial energy, a lot of the things we need, electricity, we need to have it really hot so we can make steam to generate electricity. Passive solar, it takes, we don't get very much heat for our home. If we could take a larger area, collect the heat from that, we might do a better job of heating our home. So what this inventor did in London, he realized that they were running out of wood, and so he was trying to make heat and concentrate the sun's energy to make heat, primarily steam for electricity. And so this is a mirror that focused on this end here, and there's so much heat generated from that mirror that this would boil the fluid that then could be used to do other tasks. So that was the first concentrating solar. We have a lot of that going right now out in the Southwest. These are concentrating solars, once again, used to make electricity. All these are reflectors reflecting to this tower. That tower there's fluid running through that tower, probably a molten salt or something that retains heat really well. And then that liquid is stored, could be stored up to 24 hours and still be used to generate steam to produce electricity. Same thing with this. This is a parabolic mirrors, parabolic tube that runs through, and the sun hits this and reflects back on that tube that's full of liquid. That liquid then is heated. We can store that liquid. We can use that liquid to produce steam. Now we switch gears significantly, because now we're taking the solar energy, and from the solar energy not going to solar thermal that we can use for heating our homes, or solar thermal that we can use for generating steam, which generates electricity. Solar photovoltaic. That is taking the sun's energy, the photons of energy, and directly making electricity. So this is done right now with types of solar crystals layered together, and the combination of those layers creates a flow of electricity. Right? So all we have to do is shine the sun on the solar panel, and that panel now produces electricity. So one of the nice things about solar PV is that it is scalable. I have here a little solar charger that can be used for camping. You take it out on the road with you, and it will charge your iPhone. It's got a little charging port in the back with USB, and you can take that this small. I'm producing electricity with that, which is pretty cool. Just took it on a camping trip. It seemed to work okay. provided we had energy storage. We'll talk about that in a second, but solar PV produces electricity, but it doesn't store electricity. It gets put out on the grid. And so you have to be thinking about that too. So we have scalable solar. We can go from a size like this to a rooftop scales where we generate enough electricity to power our home, or we can do super large acres and acres of solar panels that will be used to put electricity onto the grid. These panels are about 20 to 25% efficient. So, 20 to 25 times more efficient than plants at capturing energy from the sun, and it produces electricity. Most of our systems, solar PV systems, that we use on homes, say are the solar panel. We have the solar panels produce direct current, and what we use in our homes or on the grid is alternating current. And so what we do is we have a converter to go from DC to AC, and that is tied into our home, along with electricity from the grid. So because we like using electricity at night, our solar panels would not be much use to us if we didn't. I mean, they'd be used to us during the day, but when we have a need for electricity at night, most systems will use electricity from the grid at night. We can go off grid, where we would say, we're not going to use this grid system at all. We're going to have our own battery storage. We're going to generate electricity during the day. Some of that will be used, some of it will be stored in a battery, and then we're going to use that battery at night to power the rest of our house. And there can be a combination where we have solar energy generated. We use it in the home during the day. We can store it if we need to. So if the grid somehow fails, we have this battery backup storage system in our house. So we have a combination of the solar panel, the electric grid, and batteries. Obviously, this one is the most expensive. This is the cheapest. This is also expensive because of this battery storage. So in closing, I just want to talk a little bit about the future of solar energy. One of the concerns is climate change. Climate change is going to change the amount of solar irradiance hitting the earth in certain locations. Areas that are going to get more rain are going to have solar panels, solar farms that produce less electricity. So if you're managing the grid and you think that the solar panels are going to put out this much electricity and it turns out that they don't because there's more cloud cover, you have a problem. There's also concerns about more wildfires, more smoke. A couple years ago with California and a lot of wildfires out there, they were super dependent on solar energy, but they couldn't get the solar energy that was predicted because of all this smoke. So the second thing is new materials and recycling of old materials. We're always concerned about recycling, the limits on our minerals that we need for the solar panels. So we are thinking about what types of materials are available, maybe a little less harmful to the environment, or can be recycled easier. So we're thinking about that. There's a lot of research in that area. Making panels higher efficiency. So the same panel, but higher efficiency would be better. That means there's less square meters or square feet of panel needed. This is one way to look at it, but the other way to look at it is maybe we want lower efficiency panels, but panels that the electricity production costs less. So we're not looking for the most efficient solar panel. We're looking for the cheapest kilowatt hour. If that cheapest kilowatt hour can be done by a plant that's only getting 1% capture of solar energy from the sun, that'd be great. Or some thin films where we can do a larger area. If it's cheaper per kilowatt hours are cheaper, that's what we're going to go with. So I think we're looking at both of those things, higher efficiency panels and then panels that are just really low cost per kilowatt hour. And then there's going to be a lot of discussion here about integration with storage. We talked about solar PV only generating electricity when the sun is shining. What happens when there is no sun shining and we still need electricity? That's where we have to combine solar energy with some sort of a battery storage system. So there's a lot of effort in that right now. Anyhow, thanks for watching. Hope you enjoyed it. Anyhow, thanks for watching. Hope you enjoyed it. So, thanks for watching. Thanks for watching.